Hello, everyone. This is Jeffrey Hill, executive editor of Via Satellite magazine. And this episode of On Orbit will actually be the audio rebroadcast of our latest Future Space Economy webcast on the James Webb Space Telescope. Before we get started, I just want to let you know we had some technical issues on the episode, and we kept losing Scott Willoughby from Northrop Grumman due to some connectivity issues. It just happens midway through the episode, but by the end of it, we figure things out and the connectivity's fine, and Scott and I have a great conversation. So just wanted to apologize for that ahead of time. I also want to thank our generous sponsor for the Future Space Economy webcast series, MDA Space. Very much appreciate their support for this educational series. So thank you so much, MDA Space. And now on to our episode. Hello, everybody, and welcome to this episode of Via Satellite's Future Space Economy webcast series. My name is Jeffrey Hill, executive editor for Via Satellite magazine and executive chair of the Satellite Show in Washington, D.C. Thank you all so much for joining us. Future Space Economy webcast series is an educational series supported by MDA Space, a trusted space mission partner to the rapidly expanding global space industry with a 55-year record of pioneering technology and more than 450 successful missions. We thank MDA Space for their support, enabling us to produce these educational webcasts on the future space economy. Today's episode is titled Unveiling the Universe, How NASA's James Webb Space Telescope Changed Our Understanding of Space. Very much looking forward to talking about this. If you all remember JWST launching in Christmas Day in 2021, a very exciting time. And after a very, very long and exciting development process on this very powerful tool that we have in space to study the way our universe and other universes work. And since launch, JWST has clearly captivated the public with these incredible discoveries that include dying stars, distant galaxies, and possible signs of life elsewhere in the universe. And in this episode, we're going to explain the history of the JWST project, its journey through creation and into space, its breakthrough findings and potential follow-ups that could build on its success. So with us, we have two very, very special guests who are directly tied to the JWST program. First, we have Dr. Bhanu Sood. He is the Deputy Chief Technologist at NASA Goddard Space Flight Center, where he leads NASA Goddard's internal research and development program. He's won numerous awards throughout his career, including the NASA Exceptional Achievement Medal and the Robert H. Goddard Award for On-Orbit Anomaly Resolution Methodologies. And he is also an NRL Edison Patent Award winner. Dr. Sood's other roles at NASA have included Division Chief Engineer, Agency Program Manager for Training, and the Risk Assessment Process Owner for Microelectronics on a long list of program spacecraft, including JWST. So Dr. Sood, thank you so much for being here. It's good to have you here. And we are also joined by Scott Willoughby, Vice President Program Excellence at Northrop Grumman, where he oversees responsibility for program execution processes and the non-advocate review process. Northrop Grumman was the prime contractor selected to build JWST for NASA, and during this time, Scott served as the Vice President Program Manager for the James Webb Space Telescope and oversaw all aspects of the program to include total systems integration, design, development, and delivery. So Scott, thank you for being here as well. It's great to have both of you who are on this webcast who work directly on JWST. And we have a lot to talk about throughout the hour, but I want to let everybody know who's in the audience. We would also love for you to be a part of the conversation as well. If you have questions for Scott or Bhanu at any time, you can submit them using the Q&A function. It's on the right-hand side of your interface. You select Q&A, and you can send those questions to us. I will facilitate the Q&A. I'll ask those questions for you. I won't reveal your name or your company. And I like to try to weave those questions in throughout the discussion as we're having it, if it's relevant to what we're talking about. So I will pull those questions from the audience. If we don't get to your question, or you ask a question that maybe is on another topic that either Bhanu or Scott could answer, we'll have them reach out to you and answer offline if they can. So submit those questions anytime, and we'd be happy to have you part of the discussion. So lots to talk about. I'll start with you, Bhanu. Thank you so much again for being here. For those of you who aren't familiar with maybe the history of JWST, could you take us back in time and explain what drove the scientific needs for JWST when it was first conceived?
Sure, Jeff. Good afternoon, good morning, everyone. And Jeff, let me just start out by saying thank you for inviting me. Thanks to Via Satellite for organizing this very insightful webinar. Hopefully we'll all learn something from this. And Scott, thank you for being here as well. So to your question, Jeff, really the driving scientific need here was to create what scientists have always called the first light machine, a telescope that would be capable of observing the earliest stars and galaxies that were formed right after the Big Bang, which was about 13.8 billion years ago. And the JWST was conceived as a successor to the Hubble Space Telescope with a primary scientific mission to observe this early universe. Now, from there, the infrared focus for JW was determined by its main scientific purpose, which was to observe this highly redshifted light from the earliest cosmic structures just after the Big Bang. As these ancient stars and galaxies started to move away from each other at close to light speed, the light, the visible light from these was Doppler shifted towards the IR spectrum. And so that really determined and drove the infrared focus. And this required developing a telescope that could operate in IR with unprecedented sensitivity. So that IR requirement then created the telescope's most significant technical challenge, I should say, which is the need to operate at extremely cold temperatures. Here we're talking close to 40 Kelvin or minus 233 degrees centigrade to observe in the IR without interference from any of the telescope's own components or heat. And so this drove the development of the most innovative sunshield designs, the cryogenic systems, including some of the specialized cooling for example, for the mid-infrared instrument, which required cooling down to single digits, 7 kelvins. And the telescope design itself evolved to include 4 major science instruments. These included the near-infrared camera, we call it the NIRCam, the near-infrared spectrograph, NIRSpec, the near-infrared imager, and stillness spectrograph, and the mid-infrared instrument, also known as the MIRI. Each of these serving specific observational needs across different infrared wavelengths. And so these instruments used advanced detector technologies that we had once developed and used on Hubble for its wide field camera instrument, WFC3. Along with these, JWST's 6.5 meter segmented primary mirror represents another scientific requirement, which drove innovation. The need for a deployable mirror significantly larger than Hubble to collect enough light from distant faint objects. You have to remember, astrophysics is a photon-starved science. So we needed these huge deployable mirrors to collect this light. And this required developing new integration and testing procedures, including extensive cryogenic testing to ensure that the performance was optimum at these operational temperatures. And so through years of development and testing, and with eventual launch, as you said, Christmas Day on 2021, JWST remained focused on its primary mission: do that transformational science and change our view of the universe by observing first light of the cosmos.
Well, thank you so much for sharing that information with us, Dr. Sood, about what really drove that. Science really drove the creation and conception of this program, and it's interesting how those needs, the scientific needs, evolved over time. as you explained here. Scott, I know I just saw you jumped off and back on. I hope you're back here with us. If that happens again, just keep trying to log in, and we'll get to you. But Bhanu just explained the science that drove the need to build the JWST. So NASA then puts out a request to build the JWST and selected Northrop Grumman for back in 2003. And from the manufacturer's perspective, what were some of the unique challenges in building this spacecraft to this scale and with such a unique design? What were the components available to meet those scientific requirements at the start, or did you have to invent anything along the way? Just talk about a little bit about the concept here.
We had to invent. So I think the best way to convey to folks, how audacious it was to meet those science objectives that were about this old light, right? 13 plus billion years old, is that you needed a telescope bigger than we had ever done before, which to date was constrained by how big the top of the rocket was or how big a shuttle bay was, right? But that wouldn't cut it, right? An optic just the size of Hubble's, which is completely impressive, 2.4 meters, wouldn't be enough to collect these photons. And I love explaining it this way: when you are collecting photons, out there in space, it's kind of like on the ground catching raindrops. And it doesn't matter how deep your pool is if you get a half inch of rain. It matters how wide your pool is, though, right? If you get that half inch of rain as wide. So the wider the mirror, the more photons you're going to catch, because we're catching them like raindrops. So the scientists eventually settled on, if you give us a 6.5 meter optic, we're going to be able to do the job. It turns out the fairing is only 5 meters across. So we got a mirror bigger than the top of the rocket. We had to build a segmented mirror that would be folded up for launch and then deployed on orbit. And then he mentioned about infrared light. Well, the trick there is we all give off infrared. Every object is giving off infrared. Our own spacecraft is going to give up, infrared that could basically drown out, right? Be noise in the system for a photon that's 13.5 billion years old. So we had to get cold. And one of the major ways to get cold was to deploy a sun shield underneath this optic. We couldn't put it in a can like Hubble, because like we said, the mirror is already bigger and it had to fold up. So we decided to deploy like a parachute, in case an umbrella, a sun shield the size of a tennis court. So 25 meters long by 12 meters wide, right? And so you have this optic bigger that has to fold. You have a sun shield that has to deploy. That sun shield alone had 90 cables in order to get it into its final position. And it was held to structure for the launch, that violent, first day or first few minutes of getting onto orbit by 107 non-explosive actuators. All of those represent a single point failure. If they don't separate, it's stuck. So those were two of the biggest challenges. You had to get bigger than ever before, and then you had to get colder. Just by reference, colder, we ended up running the optic close to minus 400 degrees Fahrenheit. It was around 38.
Oh, I think we lost Scott again. Well, we'll have him continue when he gets back. I think we're just having connectivity issues on his end. Bhanu, while Scott's trying to jump back on here, can you talk about how NASA's partnerships came about initially with there he goes. Back. All right, Scott, we'll pause that question, Bhanu. We'll get back to it. Good. Scott, let's take off. Let's get back to where you were. Yeah,
it was in terms of the cold. Just one figure of merit to hand off is the hot side of Webb was about plus 200 degrees Fahrenheit. The sun always coming in on one side of the umbrella, and the cold side was around minus 400. So we created a 600 degree Fahrenheit differential in order to run this optic cold enough to detect the earliest photons ever in the universe.
Yeah. And we'll take a look at that picture of how, we'll get to that in a minute, of the final form of this thing, and just really like the scale of it is really impressive. I had the good fortune of actually seeing it in the test room at Greenbelt. It was huge. I mean, it's a massive spacecraft. Bhanu, can you talk, as I said before, can you talk about how you were able to bring together partners like Northrop Grumman. How did those come about initially? And also, what's the value in doing big projects in partnerships with other organizations and groups?
Sure. Yeah, partnerships and these joint efforts are really vital. And JW is no exception. It is really the result of a global effort, I should say. Even though NASA led the mission, but both the European Space Agency and the Canadian Space Agency played key roles. ESA not just provided the Ariane 5 rocket that launched JWST, but also contributed major science instruments like the near spec I mentioned earlier and part of the mid-infrared instrument, the MIRI. Those were essential for JW, especially given ESA's strength in IR technology. The Canadian Space Agency brought two incredibly important tools to the table: the Fine Guidance Sensor, which helps us point Webb with extreme accuracy to do these scientific measurements for these photon-starved measurements, and the other instrument that helps us study everything from distant galaxies to atmospheres of exoplanets. So this wasn't just a budget sharing exercise with the European Space Agency and the Canadian Space Agency. It was about bringing together what each of these agencies had, their different areas of expertise to make the telescope better than any one agency could have managed alone. And but these collaborations just didn't stop at the borders. Of course, we brought in universities, private companies, large partners such as Northrop Grumman, and engineers from all sorts of disciplines. So the creation of JWST is a remarkable story of collaboration all across the U.S. as well. More than 100 companies joined forces to bring this telescope to life. Major players like Northrop Grumman, Ball Aerospace were instrumental in building the telescope's systems, with other companies providing essential testing and equipment facilities. The project demonstrates the powerful synergy of diverse expertise, integrating optics, cryogenics, mechanical systems, data systems, and exemplifies how collaboration not only meets technical challenges, but also fosters groundbreaking innovations. And because of these efforts, JWST is unveiling these cosmic wonders and expanding the way we understand our universe, paving the way for new discoveries that shape future space exploration. I'd be remiss not to mention our partnership with the Space Telescope Science Institute, STSI, STSI, right here in Maryland. Most importantly, they operate the telescope from their JWST MOC here in Baltimore. But they also coordinate the selection of science programs. They manage the grants, proposals. They provide software for data analytics and calibration. They push out a lot of the data to the public archives and even train scientists on how to use the telescope. And so nearly all of our public communication about Webb is done in conjunction with the Space Telescope Science Institute. And as you might imagine, that's the partnership that mostly enables the research and the results, which then brings academia and commercial applications for all the wonderful ideas and high-tech advancements that we'll continue to see for many years. But there's one more thing. In addition to the spin-ins and the partnerships, we should also acknowledge the immense commercial impact of the technologies that were developed for the James Webb Space Telescope. For example, the measurement technologies developed for the JWST's precise mirror segments, the ones that Scott was alluding to, was adapted to enhance LASIK eye surgery. Think about that, allowing for more accurate measurements of eye curvatures. So this exemplifies NASA's long tradition of technology spin-offs, with James Webb's innovations extending beyond astronomy to benefit everyday life, demonstrating how the pursuit of space exploration continues to advance other fields ranging from medical imaging, vision correction, to material science, computing, data analytics, and much, much more.
Excellent. And just to illustrate how many partners there were across just the United States, I believe we have a visual of all of the partner facilities. So if we could show it, yeah, these are just project facilities in the United States, and this is just an illustration of just how many collaborators and how many partners there were on this project. Scott, just asking you to chime in here on the importance of these partnerships. Is JWST really an example like the ISS of? It's impossible to do these kinds of projects alone, right? Like
you wouldn't want to, because
right.
There are experts. So leveraging them is the best and the quickest way to get where you want to go. Take the mirror technology. There's a map that NASA had plotted the journey from the first mining of beryllium powder in a mine in Utah to like forging it into a blank to expert machinists in Ohio and Alabama, right, that had to start both machining and then eventually back to California to polish, and then to New Jersey to put gold coating on, and then to Alabama to get tested, and back to Colorado to get tested as an assembly, and then eventually to Goddard, and then to Houston, and then to Redondo Beach, at Northrop. That's just a small part of what it took to make a beryllium mirror segment. We made 18 of those, but you want to leverage the best of the best, right? You want to pull in the strengths of what you have, and that's what happened, both both nationally and internationally in this. And a lot of people got a lot of frequent flyer miles to go, follow the hardware. It was incredible, right? There were people that were dedicated that had jobs on the East Coast living on the West Coast, right? Because their hardware was there working, right, with the experts, and watch it come to fruition. So it was an incredible journey, but every one of those dots represents somebodies that really were experts in their field.
Excellent. I'd also like to bring up an image of the JWST rendering in space. We want to talk a little bit about how it functions a bit. Yeah. And there it is. That's off of the courtesy of NASA. Scott, I wanted to ask you, I'll start with you first. JWST took a long time because this is brand new pioneering technology. Scale is unique. You had multiple partners. Just the size of it required a lot of adjustments to all of the infrastructure, from transporting it to launching it. Yeah. Now that it gets to that finish line and you see it in its final form, what did you think of it? Did it meet or exceed your expectations? Something you've been working on for so long, and when you were talking to people about it, like, how do you describe it?
It was a fascinating journey, because from 2003, but you really can go earlier than that, right? When folks were drawing pictures on cocktail napkins of different artists, call it renditions of what it should look like. And of course, it didn't exactly look like that, but it evolved towards this big 6.5 meter optic of 18, honeycombed, hexagonal patterns together with the big sun shield underneath it, that umbrella that I says is the size of a tennis court. It exceeded expectations, actually, even in the form of technological beauty, which you don't think of when you engineer things. Spacecraft, they go live their lives on orbit, and you're not thinking of how they look. But people were wowed by just the look of it. It wasn't with intent, but it was. When you take a 6.5 meter gold-coated optic, right, and then you hang it from the ceiling of Goddard, right, or deploy it cup up at Johnson, or put it together with this sun shield, right, at Northrop Grumman, it's awe-inspiring, right? The gold coating is literally down in angstroms. It would be only a golf ball or two worths of gold, right, because underneath there is a beryllium substrate, because those beryllium behaves very well, right, at these cryogenic temperatures, near -400. And then you have the silver-looking, sun shield. Well, those are all coatings that are doing a thermal job, right? Meant to either absorb and then fan out and bleed out heat, right? So it didn't get from the sunny side to the mirror side. So Webb in and of itself was a work of art. There was a point in time where NASA invited artists to Goddard to see the optic in the high bay. And literally as this inspiration, right, in science, technology, engineering, art, right, in there. And they came in and not only drew pictures, I think there was a tattoo artist, I think people wrote music about it. So when you see it, you feel in awe. But then we packaged this thing up to ship it, right, on a boat. Never had a satellite go on a ship before, to get it to French Guiana, from California through the Panama Canal, to come in there in this very compact form, right, that fits only 16 feet across. And inside of there is 344 single point failures that required a level of perfection that really was the human journey, right? These were people putting cables in, putting fasteners in, attaching the last wires, right? Making sure that, signals got from point A to point B. And we figured that somewhere in the order of 10,000 humans were engaged in this, and upwards of close to 100 million, hours of labor that went into this over the span of an over 20-year journey. So you actually see, it's just evidence of what humankind can do when it puts its minds and its hearts into it.
Absolutely. And I think of those 10,000 people involved in the transportation of this thing, and just very grateful for them, because I can imagine, I could not imagine the stress of being part of that team, but just knowing how ready to go they were, and just how with all of these potential points of failure, how this thing came about is pretty incredible in itself.
A short aside or an anecdote: the truck driver who drove the mirrors around the country, NASA flew that person to French Guiana to be the truck driver that took it from the dock to the building, just so somebody else didn't drive it.
Yeah, well, yeah, absolutely. You want to put it in the best hands, right? Yep. Best hands possible. Bhanu, I'll ask you the same question. You see this thing about to launch. It's been a long journey, and you worked on it yourself. Like, what do you think of it when you see it ready to go in its final form, ready for launch?
Yeah, we continue to see. That was inspiring. My side story. I've several touch points on Webb, but the most exciting one was when I was signing off on the final ODAR and end of mission plan. I was the Goddard signatory there, and so to have it all come together like that, and before we were ready for launch, that ODAR became one of those foundational documents for us to ensure that as it was being deployed, taken towards its Lagrange point, we would have minimal orbital debris introduction, and which it did. But it was exciting to see it all come together like that.
Awesome. Scott, just for people who are not familiar with the science, or not engineers, like we talked a little bit about the scientific need that drove JWST, how it was built. Can you give us an overview of how it operates in space? How does it create and produce the images that you see on TV or on the web when you're reading about the news on NASA?
So a couple fun parameters. Bhanu mentioned the Lagrange point. First of all, it operates 1 million miles away from Earth, right? We think of, all the satellites that surround Earth from, literally just a few hundred miles away, like the Hubble and the space station and how high it is, to geosynchronous orbit, which is 22,300 miles. Well, the moon is 250,000 miles, and Lagrange point 2 is 1 million miles. So we're 4 times further than the moon, and we actually follow the Earth around the sun. We do a 365-day year.
Oh, I think Scott dropped off again. Can you pick up, Bhanu? Can you pick up on where he left off about how it produces images, and when Scott jumps back on, we'll have him.
Yeah, but why don't I talk a little bit about that, and then maybe even what has Webb really changed? How has it changed the way for us in our study of space? So, our approach to studying the cosmos since the Webb made its operational debut in 2022 has fundamentally transformed. The unprecedented IR sensitivity and the resolution that Scott was alluding to have allowed our astrophysicists and astronomers to peer deeper into the space and time than ever before, challenging existing theories, opening new frontiers of exploration. And I say we're writing new textbooks based on the science that Webb is delivering. And one of its most significant impacts, I should say, has been its ability to observe the earliest epochs of the universe. In 2023, The telescope discovered 6 massive, what we call universe breaker galaxies dating back to just 500 million years after the Big Bang. So these galaxies containing nearly as many stars as the Milky Way have challenged our understanding of how the galaxies evolve, since they shouldn't have been they shouldn't have had enough time to grow so large in so little time, according to our existing theories. The telescope has also made groundbreaking discoveries about supermassive black holes in the early universe. Webb has twice broken records for detecting the oldest black holes ever observed, providing crucial insights into how these cosmic behemoths formed and influenced galactic developments in the universe's infancy. Perhaps I think the most profound, Webb's measurements have intensified what astronomers call the Hubble tension, a discrepancy in measurements of the universe expansion rate that threatens to overturn the standard model that we've been using for cosmology. The Webb's precise observations have yielded a cosmic expansion rate of 74 kilometers per second for every megaparsec, aligning with Hubble's higher measurements rather than resolving the tension with the lower rate observed by the Planck satellites. So these discoveries and many more demonstrate how Webb has not only answered existing questions, but has raised entirely new ones, challenging our fundamental assumption about how the universe evolved and potentially requiring new physics to explain our universe's behavior as we're seeing through Webb.
Thank you so much, Bhanu. I know, Scott, we have you back. Bhanu was just starting to talk about how James Webb Space Telescope has changed science and how what the impact of some of those images are. But you were talking about how those images are produced and delivered back. So if you want to finish your answer, then we'll jump. We actually have some examples here that we can ask.
You guys are so smooth. This is.
Oh. I apologize to our audience for I think Scott's having connectivity issues and we keep losing him here. So Bhanu, let's look at a couple of example images here from James Webb, and we can talk about those. So this is one that we saw in the news recently. Can you talk about, you see an image like this from JWST, and what does this tell us about our universe?
Yeah, so I'll acknowledge as an engineer, I continue to be wowed by these groundbreaking images Webb is delivering, and the everyday discoveries it's enabling within the astrophysics and astronomy fields. And as I said, rewriting or continuing to rewrite the physics textbooks. This particular image, I'll have to go back and read up a little bit more on this and become smarter. But the Webb is the most powerful telescope that we've ever launched, and it's continuing to provide these sharp images at a higher sensitivity and providing images like this. So given its sensitivity, Webb is pushing all areas of science into new regimes, often more so than we anticipated. This means that astronomers have to develop new theories now. What we're seeing on the screen, to explain Webb's observations rather than relying on testing previous hypotheses and existing models. So, I think is Scott back, or did he?
I think he's trying to get back in. He's jumping in and out here.
This is just one example, but JW has revealed so many more bright and big galaxies and black holes than we expected to see in the early universe, which challenges previous models and raises new questions about the rate of galaxy formation in the first hundreds of millions of years of the formation of the universe. And even closer to home, not just in the far distant galaxies, within our solar system, Webb has found water vapors, signatures around comets located in the asteroid belt. The observations from JW have confirmed for the first time that water ice from the primordial solar system can be observed in that region, in the asteroid belt region, which is a major finding to help us better understand the history of water distribution in our solar system and how water may have been deposited on Earth in the past. So unlocking and answering questions about the far distant galaxies, the origins of the universe, but also telling us about water distribution here in the solar system.
Okay, while we're waiting for Scott to jump back on, we have some questions from the audience we can go to. One question here. There you go. Scott, are you back on?
I think.
Okay. All right. Well, Bhanu, let's see how many of these audience questions we can answer while we hopefully figure out what's going on with Scott's connection. First question here is going back to how you were testing JWST during the building process. Scott mentioned all of these potential points of failure with the complexity of JWST. How did you assess all of those potentials for failure? What steps did the partners take to maybe address the risks during the process?
Sure. Scott alluded to the non-explosive actuators as being, one of those single point of failure. And I can tell you, when I first started working on Webb, that was one of the things I got to work on, which is to look at or conduct these trade studies, both from, paper exercises to look at parameters, but also conducting physical testing and simulations using finite element analysis on these various form factors of the non-explosive actuators to understand their behavior and reliability. I had the opportunity to work very closely with some of the reliability team members in understanding what are the procedures they're using to evaluate the reliability of these NEAs, and how would the NEAs, what would be the critical failure modes, mechanisms, and how would these mechanisms play out during its on-ground testing, during ascent, deployment, and during the final release. So that sequence of events in the reliability prediction was fascinating. Again, these were single points of failure with no redundancy. So every single one of these NEAs had to work and do this choreographed deployment on schedule to make it work. So I can go on and on, but Scott is back, I believe. So
I'm on another device.
All right. So Scott, hopefully this one works out for us. We were just answering an audience question about, or when you were talking about the build for JWST, you were talking about how many potential points of failure there were on such a massive instrument. How did you assess the potential for failure, and what steps did you take to address the risk? So I'll let you chime in for this question.
Yeah, I think the greatest part was certainly in any level of thing that you're engineering, there's what's called margin, right? How much do you, in effect, over-design the device so to not just meet its performance requirements, to be robust enough in case something isn't ideal. If it's too cold, if it's too hot, if the strength of the spring isn't so strong, will it still deploy? So with Webb, one of the greatest things we did was all the way early on in the design phase, design what we'll call our factors or safeties and margin was. And it was far greater for anything that was a single point failure or was, in a critical path than it would be for a normal box. Because you don't want to over design everything, right? That takes expense and it takes time. But we necessarily for something that goes 1 million miles away. I had a few astronauts who serviced the Hubble say, I can't go out there to Lagrange Point 2, right? I'm not going to get that far, so this one has to work, right? We had no means of sending an astronaut or robotically even servicing at this point in time. So we did that robustness. And then, of course, we tested these things as much as you possibly could in an environment on Earth, right? And you put them to qualification levels, colder, hotter. You put them in a stressing environment that was greater than you would see. So when it all worked flawlessly, it's because we really designed this thing so that, it has to work in this window, but it was designed to work in a window, that was bigger than that. And you do that just time and time again. And then the very last bit is workmanship, meaning does somebody put in the right spot, right? Make sure that the wire goes through the right clip. And then that was the level of, both engineers overseeing, technicians, and then quality mission assurance, overseeing those. And basically all the people who worked on Webb had you had to leave your ego outside the door. You had to be prepared that people were going to challenge and question, did you do that right? I need to hear the torque wrench click. I need to see the wire in the cable, not just say you said it was so, and go and look at it in my own eyes. And when the mission is greater than the self, that's exactly what happens. The team really gels. So, the very final step just came down to the personal commitment of the folks who put it together.
Thanks so much, Scott. While we have you on a connection, it seems to be hopefully stable here. I want to go back because we asked you about how James Webb Space Telescope works in space. And I want to ask it again in this form of this question here from the audience. Can you give an explanation that students can understand? How do we take these images from JWST and how are we able to tell how old things are in the universe? How do we use the redshift to determine distance and age? And just go back to how this thing works in space.
Yeah. So when you're collecting light that's far away, you're like an archaeologist. So you're going back layers and layers and layers, right? So you're digging, and the further you dig underground, the older you're getting, right? So further back in time, and voila, you find that dinosaur bone, right? So Webb is like an archaeologist, magnificent weapon in space, instrument mechanism where it's finding stuff that's older by finding things that started further away. So that's the first kind of idea of looking back in time. So what happens is a photon from a star that was further away from us took longer to get to us. And then when we capture it, like an archaeologist, you're capturing it though with the information when it left its star, right? So this photon left, so you still have that fingerprint, and that's what the instruments do. It collects the photon and it brings it kind of to either a camera or what's called a spectrograph, the things that break it up into wavelengths that at different wavelengths it tells you different things about its fingerprint. So in a way that really a simple person is we're going by finding things older, by finding things further away. And then when we get them, we look at their DNA and their fingerprints with instruments, and that tells us something about it. It tells us the chemistry of that star when it first formed. Because one of the missions is very interesting, right? I always like this story when I talk to a lot of students is if you were only 13.5 billion years old, you'd get an A+ in chemistry because there was only hydrogen and helium in the universe. And so if you only had element 1 and 2 to remember on a periodic table, chemistry would have been pretty easy for everybody. But now we know there's much more complicated periodic table. That's because hydrogen and helium were the fuel and the very first stars that created fusion reactors that built up all these other elements. So when you look back in time and you see, very early stars, you see how that chemistry, you could see things before, right, a star exploded into a supernova. That's where golds and platinums come. So you wouldn't see those on young stars, right? You would just see up to like carbon, maybe all as high as iron in there. So that's what we're doing. We're finding things that are further away, so they're older. And then we're finding things that tell us what they were like when they left. And then we use that into scientific models to say, hey, we predicted it should look like this. It's different. And then that's when the scientists almost get more excited, is when they find out something they didn't expect to see, almost as much as when they convince themselves they saw what they predicted.
So if you'll both chime in here and answer this question, what do you consider the most important discoveries from JWST here in the first part of its life here? What are some of the most groundbreaking images that it's taken? I'll start with you, Bhanu. What do you consider like the real milestone achievements in terms of discovery? I think you're mute. You're on mute.
Thank you. Yeah, I love the analogy Scott used about the archaeology, how they're removing layer by layer and looking further out in time. So I'm going to use that as a springboard and say what I said a few moments ago about, not only are we learning, about the origins of the cosmos and, those few million years immediately after the Big Bang 13.8 billion years ago, but we're also learning, getting new information about our solar system here, from observing Jupiter's previously unseen jet streams to detecting carbon dioxide on Europa's oceans and finding organic molecules in distant galaxies. So demonstrating how this technological perseverance, by keeping innovations going, can yield profound scientific rewards. The path forward for space science seems incredibly bright as researchers continue mining Webb's data while planning even more ambitious observatories. Perhaps most inspiring is how Webb represents a triumph of human collaboration, mentioned earlier about the agencies coming together, but also hundreds of commercial partners, academia, and organizations, and ingenuity, overcoming countless technical challenges to deploy this huge tennis court-sized sun shield using the non-explosive actuators, and then precisely aligning these 18 beryllium mirror segments in the harsh environment of space. That's a technological, first, I should say. And it's showing us that universe's earliest moments with remarkable clarity. JWST reminds us that with patience, cooperation, and bold vision, we can answer humanity's most profound questions about our cosmic origins.
Thanks so much for that, Bhanu. Scott, what do you, from your perspective, what are some of the discoveries that have really impressed you?
Yeah, so there's the beautiful pictures, ones that have ended up on a stamp, right, or people's screensavers now that are there that are amazing. But I talked about looking at the wavelengths of life of light and spectroscopy. The very first time we proved we can see what was in the atmosphere of an exoplanet, a planet around a star outside of our solar system, and it was just literally, it was squiggly lines, right, compared to what those would look like if there was carbon dioxide, right, or other things in those atmospheres. That blew my mind away. I know we designed an instrument to do that, but there's so very few photons that either they get blocked by the planet, which tells us the planet's there, right? Because you get this transit effect, right, of it darkening its star, or they go completely around it, right? And you get a clean photon, right, from the stars, so you know what it looks like. But the ones that just graze the surface of that planet, if there's an atmosphere there, that photon is changed by what's in the atmosphere. We actually have an instrument that has showed us we can make that atmosphere confess to us what is in it. And so it's out with all the beauty of the pictures, stars dying, stars being birthed, right? Protoplanetary disks around stars and that stuff. To me, it was the squiggly lines that prove this instrument can now interrogate the edges of planets millions of light years away, and just a few photons that go through there, they're telling us what was in that atmosphere. What did it, what absorbed, right, certain things in there. So as soon as we saw that, even though we didn't find signs of life in that first, observation, and we're not sure yet that we have, right, that takes a lot of data and scientific, analysis to get there. We proved the machine can give us that data. Now the hunt is on.
Right, exactly, and that's a nice segue into our next question, because it's still relatively early on, right, in JWST mission. It's expected to remain operational into the 2040s, which is significantly longer than was first expected when we launched it. And a couple of people from the audience have asked the same question too, like what's the future hold for JWST? How is it going to be applied over the next few years in the sort of second half of its mission, and what can we expect from it in the future? Let's start with you, Scott, and we'll go to Bhanu.
So there's the planned missions, right? I always like to give the simple requirements. Where do we come from, and are we alone? Mm-hmm. Turns out it was a really thick book that translate those requirements into something an engineer could build an instrument. So in that journey, I'm going to give the story of when I first started on the program, and I met with an incredibly smart scientists, and I'm an engineer, right? And I heard them talk not just with awe about the things they found with prior instruments that they were looking for. It was the serendipitous discovery of they didn't know the question to ask. But in looking at this data, they said there was this aha moment. They saw something that they didn't predict, which made them either, affect a parameter in a model. So I hate to answer your question this way. I mean, it's going to do its mission, right? It's going to search for signs of life in exoplanets. It's going to break its record over and over again, right? What is the oldest galaxy, and then the stars within that. But we don't know yet that, we're going to find something we didn't think to look for. That's going to be in that data. And then it's really going to open us up to maybe a whole new avenue, right? For science to start applying that. And I've been told that by people far smarter than me. It's that the top 10 scientific discoveries from Hubble, some great portion of those weren't what the original plan was to look for.
Thanks, Scott. Bhanu, from NASA's perspective, what's the plan moving forward? Has that plan changed? Are you expecting unexpected discoveries? Tell us a little bit about the future path here.
No, I think Webb will continue. These series of groundbreaking observations for many years to come. We're finding out through the Space Telescope Science Institute and other partners. Scientists are just beginning to unlock the full potential of Webb by defining new measurements, new observations. Scott just described how single photons through a planet's and exoplanet's atmospheres can tell us a lot about the composition or some early information about the atmosphere around those planets. So based on the current performance, we believe Webb has enough fuel to potentially operate for 10, 15, or even longer years, far exceeding its original 10-year mission lifetime. In the coming years, we believe astronomers will likely focus more deeply on these exoplanet atmospheres, as Scott was alluding to, searching for prebiotic life, biosignatures, or any other characteristics that holds promise to answer that big question: are we alone? We're going to definitely look at systems that have been observed before, like the TRAPPIST-1 system. But JW will also continue peering at those earliest galaxies, those origins of the universe, galaxies that were formed around that time, and these supermassive black holes, helping resolve some of the ongoing debates in the scientific community about the universe's expansion rates and early formation. And as more astronomers become familiar with Webb's capabilities, and the observation techniques are refined, and data analytics continues to be refined, we can expect increasingly sophisticated discoveries that build upon these initial findings, I'll say. Meanwhile, the lessons learned from JWST's development and operations will inform the next generation space observatories that we will build in partnership with our private partners and universities and other companies across the nation here. And with partnering with other space agencies worldwide. So there's a lot of promise. Webb holds. It has just started on its discovery.
Thanks, Bhanu. I know you've actually started to answer this question. The big one from the audience and also on here is like, what's next? What's the next plan? What's the next spacecraft? What's the next JWST? How do we build on what we've achieved and what we will achieve with JWST? What's next in the pipeline? So I'll start with you, Bhanu, and then I'll ask Scott.
So I'll quickly respond by saying that we have several scientific concepts being looked at. One of them, obviously, is using the discoveries of Webb. I mentioned exoplanets and answering that big question: are we alone? So if we take that and we break that down into scientific requirements, the Habitable Worlds Observatory definitely comes to mind. But there's a lot of questions from a science perspective and from a technological perspective that are still being worked on. But that's definitely one in the pipeline for us.
Scott?
Yeah, and the compliment I like to add is what Webb did was, for a long time, technologies evolve. They get better and they get better. But Webb was really a revolution, right? It wasn't any longer making a monolithic mirror a little bit bigger, right? Or moving a wavelength, to just another part of the spectrum. it created this segmented mirror, right? Which now means, how can you create bigger segmented mirrors, possibly on Earth to stow more, possibly in space to add to it. That mirror is an adaptive optic. Each one of those mirrors has 7 motors on the back, one on each corner of the hexagon and in the center of curvature, one in the middle. So it's not just a deployed optic, it's an adaptive optic. So it's going to continue to give us, the crispest images that it can. So now that you have that and you've proved these deployable technologies and segmented technologies, we're a bit less bounded, right, by just, how much can we get and, just from left to right, in a diameter of a fairing. And by the way, though, fairings are going to get bigger, with the bigger rockets in there. So you take a bigger fairing and something that you can scale. It's actually incredible to think, that how far we've been able to now to push the bounds, right? Because to get to the even more audacious science of not just looking at atmospheres on planets, you want to look on the surface of a planet, right? Humankind is going to want to say, can I stare at that surface and see the rocky, or the oceans world and do that? Well, you need even a much bigger telescope. Some say, twice as big as Webb. And you can't just have that telescope. You have to fly it with a form of an occulter, because you have to knock the star down, right, that planet is circling, because Earth-like planets in the Goldilocks zone are kind of close to their stars, not too close to be too hot, but not super far away where they become, icy planets. So you have to knock that light down. So I believe that's where the science will go. It will go to take advantage of the technology, right, that's presented itself, to get something that, can both interrogate atmospheres, but then look on surfaces, of planets. And it's just a natural progression where our curiosity will go. So then the technology will follow that.
I tell my 7-year-old son that it's so exciting that he's living in a time where it is very, very, very possible that humans will discover they're not alone in the universe in terms of life, that just the discovery of any living organism on another planet, that we're able to make those kinds of discoveries in his lifetime is very exciting, just compared to how long we've been on this planet, right? There's a couple of, before we wrap, there are a couple questions that came into the audience, Scott, when we were having some connectivity issues that were related to the operation of the JWST. I just want to give you a very quick opportunity to answer those questions. One question was, can you explain what the challenges were of putting JWST in the precise Lagrange point? Yeah,
so it's the complexity was mass, to be honest with you. To get off of Earth is still hard. It's still the rocket equation. So when you have to go 1 million miles away, then you had to make something more lightweight. So just here's the reference. Hubble is a 2.4 meter optic, single piece of glass, 25,000 pounds. Webb, 6.5 meter optics, about 7 times the collecting area, 14,000 pounds, right? Mm-hmm. So we had to be lighter weight because it was still hard for us to even conceive of not only getting off Earth, but successfully out 1 million miles. Once you get there, I think it's what's called an unstable equilibrium. You can, if you kind of get in there, but you don't hold to a point. You actually do a halo orbit about that point. And so you have to use fuel on board. That's one of the life limiting things of Webb, is that you have thrusters that do course corrections and they kind of keep you in there. It's called station keeping. But we've had no trouble maintaining that orbit. Really, after we got over the mass, we weren't the first, maybe the fourth or the fifth, I don't know, but Herschel and Planck and Gaia, there's a few others out there. So it was somebody had trailblazed a path there. Once we got lightweight enough to get on top of the Ariane rocket and make it there, we knew the orbital dynamics of where we wanted to get, and we know how to hold that orbit, and we've proven that for 3 years now.
Excellent. And then another question here, and I guess this is for both of you. I had mentioned in one of my questions, and it's that JWST is expected to remain operational possibly into the 2040s. Somebody asked, so they've heard others say that it could last longer than that. Could it be refueled via groundbreaking technology? Is that possible?
You want me to take a crack at it, Bhanu? So it is going to be most likely fuel limited. There are still things that will decay, like the focal plane arrays, and at some point in time, you just can't do anything about it, right? They're exposed, so they'll start losing their sensitivity. The mirror is subjected to micrometeorites, but honestly, it's such a big mirror. Small imperfections just means you just have a little bit of less if the photon goes, precisely there. But you have to use fuel for a few reasons. One is the station keeping. You have to do that. The other is, as you're pointing and body steering this whole thing, you use reaction wheels, and they spin up momentum, and they enable you to slew. Well, you can only do that in one direction to a limit. And then you have to unwind the wheel. Well, to do that, you don't want to unwind the wheel just all by its own. It'll spin the telescope. So you fire the thrusters in the opposite direction, right, of where that momentum is getting offloaded, which means you use fuel. So those two things are fuel, and then, for any other purposes that we may need to move it in its orbit. So fuel will be one. We did put fiducials on the vehicle, meaning so that something could do what's called a rendezvous and proxops, meaning so that when it gets there, it can see it. It's the type of information you need to approach something and then know how to grab onto it. But it would have to be a bit elegant. It'd have to be a robotic solution. It'd have to cut the cap off of the gas tank and do it. I won't put anything beyond what humankind can do, because we built the James Webb Space Telescope. That technology doesn't exist today. So will it in 10 or 15 years? We did make the spacecraft approachable. So that's probably the simple answer.
Thank you so much, Scott. I'm glad we were able to answer those operational questions. I know we're having some connectivity issues soon, but thank you both. Dr. Sood, thank you for being with us here. Scott, thank you so much for joining us. And thank you to our audience members. We really hope you enjoyed this discussion. And if you can go to NASA's website, you can see some of the images and discoveries that the James Webb Space Telescope has made, and some information about the future of the space science program. Thank you both. I really appreciate it. I had a lot of fun talking about JWST. Congratulations on a successful mission, and we look forward to more discoveries in the future.
Thank you, Jeff.
Thank you
very
both.
much.